Lastly, I want to talk about a couple of examples of higher order equations. So we've done mostly first order equations, and all the qualitative analysis was first order equations, but we can talk about higher order equations. We did higher order equations at length in the middle of this course with second order linear equations. And I want to go back to that, and I want to think about harmonic motion again. And now I want to think about coupled springs. So now I want to think about two masses connected by springs where the first mass is connected to a fixed point, a wall, and then there's a spring connecting the two masses. So K1 is the spring constant of the first spring that's going to pull it back to equilibrium, and then K2 is the spring between the two masses, and it's going to pull positively on x1 and negatively on x2. The spring constants turn via Newton's first law into forces, so mass times acceleration, second derivative of position. So I get these two force equations out of the physics. These two are a set of coupled second order equations measuring the behavior of springs and masses on springs that are connected to each other. To actually solve this, let me give you some numbers. I have just setting the masses m1 and m2 to be 1. Here are some spring constants. The first spring is a bit stiffer. And I'm going to start the springs at rest, but I'm going to start the second mass with some initial velocity pulling away from equilibrium in a positive direction. I need first and second derivatives when I set initial conditions for this, because I'm dealing with a second order equation. So when I Laplace transform this, I'm going to need both the initial position and the initial velocity. All right, this is what that looks like with those numbers involved. Put those numbers in, you get these equations. You sort of pull everything over to the left. This is what I want to apply the Laplace transform to. So these second derivatives are going to turn into s squareds times capital X1 and capital X2. This is the only place an initial condition shows up. There were no initial conditions for x1. There was only one for x2. It shows up here. And then these other pieces of the equations translate very, very nicely. And I get a system of two algebraic equations for x1 and x2 that I want to solve in terms of the given variable s. Again, there's a lot of work here involving splitting these up, involving isolation replacement, involving partial fractions. Do all that algebra, you get these two expressions for capital X1 and capital X2. And both of these have inverse transforms. Both of these turn into cosine functions. And what I'm going to get out of these coupled springs is the superposition of two different cosine functions with different frequencies, which is going to look a little bit erratic. It's not going to be a pure oscillation. It's going to sort of jump around as these two waves superimpose upon themselves. So when they're both at peaks, it's going to look quite substantial, and they'll cancel themselves off and have a little bit of equilibrium when one is at a peak as one is at a trough. And you'll get an interesting behavior out of these two masses of these springs in these superposition of waves. And it's cool that we can see that more interesting and more complicated behavior out of the system just by applying the Laplace transform. Here's another one, and here I've added a third spring that connects the second object also to a fixed wall. So think of a fixed wall on the left, a fixed wall on the right, and then three springs and two masses between them. What's going to happen here? Well, I'll set the masses again to 1. I'll set the outside springs to have spring constant 2, and the middle spring to have a little bit of a weaker spring. I'll set the initial positions to be 0, and the initial velocities to be going outward. So the first one is going left towards the wall. The second one is going right towards the wall. The two masses are moving away from each other. In this coupled system, what do I expect? Whether those are the equations you get if you put those numbers in. You take Laplace transforms. +1 and -1 is where those initial conditions show up. The second derivative turns into s squareds. You have to solve these algebraic equations. Again, a lot of steps, but you get these algebraic results. And this is actually quite nice. These turn into just sine functions. And the reason this is so balanced is because the spring constants measured balance each other out. We had the spring constant of 2 and 2 on the outsides, and the initial conditions were also balanced, -1 and 1. So since the system was so nicely balanced, it's actually going to oscillate pretty perfectly. This system doesn't have frictions, there's no decay, but I'm going to get sort of these opposite oscillations where the springs pull apart, then come together, and then pull apart and come together over and over again. And it's really quite lovely that I can just apply the Laplace transform, do the algebraic equation, and solve this. And that's as far as I'm going to go with examples. Laplace transforms are really the only technique we have so far in this course. There are different ways to deal with systems of differential equations, but Laplace transforms, when they work, are by far the most reasonable and convenient, and can rely on all the techniques we've already learned in the last chapter.